Why do I use this? I use it in the following. So this is the part one. The leading principle I am the this is where I think how. Now suppose that one side is easy. Let's say this is so assume A is finished and I want to show that leading I want to show this. Okay. Now because A is leading, this means A is Cartesian and the eigenvalues are negative. This part was not given. Eigenvalues are given. So you have 0 lambda 1 less than equal to lambda 2 less than equal to lambda. Now if you take a principal submatrix of size n minus 1, then by Gaussian interpolation theorem, because if you drop one row and corresponding column, then the eigenvalue of the submatrix will be here in between. That's what it says. The Gaussian interpolation theorem says if the bigger matrix has eigenvalue this, then the smaller matrix will have eigenvalues in the gap. That is what it said. So if I take the smaller matrix, it will have with the gap from here, so it will remain positive. And if you want to drop one more row and one more column with the same column, it will remain in the gap of the previous one. That will remain positive. Okay, and therefore determinant of the principal submatrix okay. Ideal na A lambda 1, lambda 2, lambda 3, lambda n. Then a principal submatrix will have eigenvalues in between in the gap, so it will remain positive. Further, principal submatrix will be in the gap, will be positive because the lowest one was positive. So any principal submatrix will have eigenvalues positive. Determinant being product of eigenvalues. Okay, so this complies. Okay, the other side, if you want to show, so assume that A is Cartesian and all the leading principal minors are positive, and I want to say A is B, positive delta. Leading principal minors means like I told you, when you take matrix like this, consider this one, consider this one, consider this one like this, and take their determinant. Those are positive. If those are positive determinant, then it turns out that it will be positive determinant. So by induction. True for n equal to 1, that is true, assume it is true for the value okay, for true for 1, assume it is true up to n minus 1. Okay. And suppose that you have a Lorentzian matrix. Star equal to f with all leading principal minus 2. Okay. Then I want to prove that this is P. Now what about A, N, N? This is what, and this is the principal submatrix obtained by deleting NH1 and NH2. Okay, consider the principal submatrix obtained by deleting the NH2 of A and NH2. Now, does this satisfy the hypothesis? Or that means whether this is Hermitian, whether all principal submatrices of this as a determinant positive, because all principal submatrices of this are principal submatrices of A, and by hypothesis they are determinant positive. Therefore, by induction hypothesis, this is believed. Because this one side is n minus 1. You have deleted one and one column, that you got column. So the matrix is smaller size. Satisfy the hypothesis. By induction hypothesis, this is PD. And because this is PD, this will have eigenvalue positive. Okay. So the submatrix has eigenvalues positive. And what are those eigenvalues? Now the eigenvalues are like mu1, mu2, mu(n) minus 1. But then A is a supermatrix, bordering supermatrix. Remember the P? A is like B here. It is a bordering supermatrix. And therefore, eigenvalues of B, well, like eigenvalues of A here, will be here only. Lambda 1, lambda 2, lambda n. Because it will be interlacered. And therefore, A will have eigenvalues this up to this positive. Because mu1 was positive, remember? Because A, the submatrix was PD. So mu1 was positive, therefore it follows that definitely n minus 1 eigenvalues of A are positive. Okay. But then remember the determinant of A was also positive. And determinant is product of eigenvalues. It follows that lambda 1 is also. Okay. This implies lambda 1 is also positive. And rate of them are positive follows from the fact that the smaller matrix was big and it was interlacered. Okay. Fine. Okay. So what I will be doing, so here I will stop. We'll see how this helps us in graph theory. Yesterday I believe sir made a statement saying that if the diameter is this, then we will have at least this many distinct identities for a graph adjacency matrix. But then you know what? If I am looking at the adjacency matrix of the graph and I am including one more vertex, that new adjacency matrix is like the bordering matrix P of the old one. So the eigenvalue must be interlaced, right? So that we will use. I will tell you how we are using how you are using these things to tell ideal of graphs. Okay, we'll talk about that. I think now I have 30 more minutes. It is up to 11. Oh, I thought it would stop 5 till now. No, no. I thought this one is over, the time is over. Okay, time is not over. Or because the time was, I thought because the time is getting over, and I, like if you did not understand it, please ask me, I will be, I will do. Anybody can read them. Okay, so this much, whatever I wanted to tell, this much is good enough now for me to talk about adjacency matrix. Adjacency matrix to your launch. Remember there is an edge, I get so AI is between one other entity that zero is the edge matrix. Real symmetric matrix, they are like particularly Hermitian matrix, so if spectral here, no problem. Now, I want to talk about the uh, okay, let me first tell you. Every so suppose that I am looking at a connected graph of 57 draw a general one. And there is something called diameter. All of you know what is diameter in a graph, or shall I define? If anybody, because I want you to understand. If you do not know, just test. Diameter in a graph, understand? Tell me. So corresponding to the diameter, so what is it now given in any 2 points? There is something called a distance. The smallest length of a path from here to here. Okay? And look at all the distances between pairwise, pair of vertices, and finally whichever is bigger, that is the diameter value. And that path I will also call as diameter. Well, like in a circle, diameter is diameter, and diameter is the number, length of the diameter. That's the way from our school days. That radius 2 centimeter and radius is radius. What is the diameter here? That means what is the value of the diameter and which part? 0.46. 1, 1, 2. Okay, everybody. Now, tell me one. Have you heard of the induced subject? Now, if I take this vertices, what is the induced subject? Will you ever get any extra edge among them? Let's say 2 to 6. Assume that, not only for this graph, I am saying, assume that I have drawn this graph. I have a graph myself. I am not showing it to you, but I am saying this is diameter. Is it possible that 2 is joined to 6 via an edge? Then it will not be the diameter, right? So I have found a path. Okay, diameter. And what is the adjacency matrix corresponding to this? Now 1, 2, 3, 4, 5. So it will be adjacency matrix of the 5. So it will look like this. 0, 1, 0, 0. How many? 5, na? 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0. This below is the submatrix of the adjacency matrix of this. Okay. Okay. Now, if this fellow I saw that has 4 distinct eigenvalues, by interlacing it will follow that that will also have 4 distinct eigenvalues. All I have to show is that this has 4 distinct eigenvalues. Sorry, cycle 5 distinct eigenvalues. So if I show that the eigenvalues are पूरा ही लेते So this has 5 distinct eigenvalues. I will show. I will show it. We will. As long as I cannot become weak, then there is no point. Nah. I will show the I have already shown. It is you. Okay. If we show that this is this, and because this is a super matrix, I can apply Cauchy interpolation theorem. It will follow that the next one will have one eigenvalue here, one here, one here, one here, one here, and so it will be distinct. At least 5 distinct, at least 5 distinct, and that will continue. So my theorem will be there. If the diameter of a graph is 5, then it will have at least 5 distinct eigenvalues. That theorem will be proved. All I need to show is that P5 has 5 distinct eigenvalues. Okay, and what are eigenvalues of P5? Now, okay, eigenvalues of P5 sometimes P5. When you draw P5, that is P5. Then whatever process I am going to follow, it will follow in general ones. Now P5 is asymmetric. Okay. So to make symmetric, what you do, you include you take 2 copies of P5. Put one vertex here, put one vertex here, and make it adjacent. So then I have sequence. I took 2 copies of P5, introduced 2 new vertices and put the joint. I have created sequence. What are the eigenvalues of sequence? Now those are all eigenvalues of sequence. 2 cos 8 yeah, to get eigen correct. That is correct. The eigenvalues of sequence adjacency eigenvalues. Eigenvalues of adjacency undirected sequence will be obtained by directed sequence. Okay. For this, you consider sequence directed. I will find the eigenvalue of this, and from here I will find the eigenvalue of that. Okay, how do I find the eigenvalue of this? Now, adjacency matrix looks like this one. 1 goes to 2, 0, 0, 0, like then 2 goes to 3, 3 goes to 4, and everything, and then 12 goes to 1. It will have a, like it will go up to this, and then the last one will be this, like this. So, directed adjacency matrix of a directed segmentation. Now, these ones I can tell you know. These are omega power n equal to 1. That is the characteristic polynomial, right? If you are looking at, so I take this left side. If you have a matrix of this form, and by n matrix this, then the characteristic polynomial of this one, try to find out the characteristic polynomial of this one. अच्छा कम से कम 4 पर निकालो. Find the characteristic polynomial of this one. The characteristic polynomial in terms of t. T is the variable. Characteristic polynomial, so that is ti minus a. Compute the characteristic polynomial of n. Characteristic polynomial, determinant of ti minus a. So that comes out to be t power 4 minus 1. That is the characteristic polynomial. Did you count on that out? I will can go a little bit of tutorial later. And this one computed. Okay, if you compute it in the some matrix, well, don't do that. There are only 2 sigmas. Okay, what is that I want to find out? I want to find out the characteristic polynomial. So that is this only. T minus 1, t minus 1, t minus 1 minus 1. Okay. I want to find out the determinant, and there are only 2 sigmas that will work up to permutations. One is the identity permutation, and the other one is this permutation. 1 going to 2, 2 going to 3, 3 going to 4, 4 going to 1. That permutation will only work. Okay, the identity permutation is n t power 4. The cycle, because it is cycle of cycle 4, therefore product of 3 transpositions, even size. Okay, so that will do that. Okay. Anyway, so this will be t power 4 minus 1. Yes, sorry, there is a t over here. Minus 1, and then in the case of C5, you will have C5 is even permutation, but you would have multiplied minus 1 power 5, that would be. Okay. So if it is 1, 1, 1, 1, then you rectify. For example, if I put 1, 1, 1, 1, then currently you will get the power 4 minus 1, because the even the odd cycle will give you minus. But if if I make it size 5 by 5, you will get t power 5 plus 1 because that C5 will become uh, even this product, so that becomes clear. Okay, and so here because I have minus 1 minus 1 minus 1 minus 1, in that case in C5 it will be. So in any case, the characteristic polynomial with the power n minus 1 equal to 0, so the eigenvalues are all nth root of unity. So what are they? First, at k so I have written, at 2n I have to write. But I am writing cos not directly. K I am telling, k I am telling, and divided by 10. And I sin divided by that is it. And then what? Then there is one more thing. This one, that is the ACN, is equal to ACN directed plus because see where if you are trying to write the adjacency matrix of this one, then you would like to put one here, one here, one here, and this one there also. The undirected adjacency matrix. This one, there will be one here. This one, there will be one here. And this one, there will be one. This one will be having one, and this one will be having one. Okay. So undirected adjacency matrix is this one. Okay. But look at that. SCM directed matrix is a permutation matrix. Every row and every column matrix is one. It's a permutation matrix, in particular corresponding to the cycle formulas. 1 goes to 2, 2 goes to 3, 3 goes to. Yesterday we were talking about permutation matrix. And for permutation matrices, their transpose are there in inverse. That is what I said. Transpose are there in inverse. Therefore, this is nothing but inverse. Okay. And hence, if something is an eigenvalue and eigenvector for this, in the inverse, the same eigenvector will work for 1 by that. That is, suppose x equal to lambda x and a is invertible. Then you multiply a inverse both sides, you will get x is equal to lambda a inverse x, or a inverse x is equal to 1 by lambda x. Of course, lambda is not equal to 0. If a is invertible, it will never have 0 eigenvalue. Okay. So, if x is an eigenvector for this with respect to lambda, then this is also an eigenvector for this with respect to 1 by lambda. The same eigenvector. Okay. And therefore, if I had how many distinct eigenvalues? I had, for example, for this 4, for n, I had n distinct eigenvalues. They are all distinct, na? The roots of unity, nth roots of unity, they are all distinct. I had n distinct eigenvalues, and therefore I had their respective eigenvectors, linearly independent. Now, distinct eigenvalues, linearly independent eigenvectors, diagonalizable, everything is fine. And therefore, this matrix, for this matrix, that set of eigenvectors will also work as eigenvector. Because you take the point vector x, earlier you were getting lambda, now for this you will get lambda plus 1 by lambda. That is the eigenvector. So, if lambda 1, lambda 2, lambda n are eigenvalues, remember this one, of SCN directed, then lambda I plus 1 by lambda I are eigenvalues of SCN on there. Because whatever were the eigenvectors, remember the n linearly independent eigenvectors, I just multiplied with them. And I checked that, okay, when I multiply one eigenvector, that corresponding eigenvalue plus 1 by lambda. Okay, and what is that? This was lambda k. Okay, this was the test. So what we were getting, that this one plus in the inverse one. Okay. So then what will be the sum? So it is essential when you are adding this is minus k, as it is minus k. And therefore, what will cancel out? This will cancel out, and you will get twice of this. Okay. That's okay. So you have evaluated this. What are the eigenvalues over here? Twice cos a pi 12. No, you are 12 na. Okay, fine. Okay, fine. 2, 4, I forgot to say. This one. Okay, fine. The denominator is inside. Oh, this is called context error. Because I was writing this, after some time this writing got stretched and I did not visualize what. Okay. Okay. So that is what is. So it is like K5 by 6 is not different, right? And so from here, I want to find out the eigenvalue of this. Okay. So Somebody please note this much, and I will continue from there. And it will be over as soon as I show that has height distinct as because that is what we wanted to show. In order to prove that if a graph has diameter, connected graph has diameter this, then that has at least that. Small announcement as far as the registration is, have changed your name, the register as you go. Have any, there's any mistake in your spelling, any mistake. But you are into technology. There's no technology, why he is missing like that small mistakes that have all said, if your application and name. Not, I'll keep it outside or I'll check. Thank you. You can say. Because if you are your certificate, you are getting the name. Depending on the case of the party. And you can also correct it.
Understand? Huh? That's what. Yeah. Shouldn't look good. But the camera looks a bit. Yeah, looks like here this is not correct. Where, but don't know how to adjust it. Yeah, where it is secret. There is some. No. Why is it? Oh, require extension? Yes, it's there upstairs. Is it there? Yeah, okay, we'll get it later then. Yeah. I think this is pulling good. I will bring them. Yeah.
Hey, Vinay, can you hear me? Vinay, can you hear me?
Now it's okay, right? Okay. Thank you.
It's coming, yeah, it's starting.
It is that area later. Is it good?
Yeah, sure. It's charging.
Okay. In this, it won't show.
No, no. Laptop is charging.
Yeah. Okay.